A lot of times when we look at a problem that has too many words in it, we sort of get glazed eyes, our eyes glaze over, and we're like, too many words, like, just give me numbers, don't give me equations, don't give me words, right? All right, but in this class, the words are purposeful, and you can get clues, you can glean clues. When you've got some of the words, then there's stuff that you can pull out of that. We talked yesterday about, as soon as they tell you something's continuous, that's an important word because it tells you some other things. As soon as you know something's differentiable, it's another important word. If it's twice differentiable, thrice differentiable, the words are important. Today we're going to talk about the unit words, the words of units, how they are important and how you can glean and learn something about what to do with the problem when you've got words. All right, so we know already from first semester that units are impacted when you take a derivative. All right, we've learned that when you do the first derivative, then that introduces time into the equation, and so you've got meters divided by seconds. And then when you do the second derivative, that introduces time again, and you divide by seconds again. And if you did a third derivative, it would bring time in one more time, and that is the physical representation. We know we've got velocity, acceleration. That would be the physical thing we call jerk, or the feeling that you have when you're, if you've either been in a car accident or you've ridden one of the, roller coaster where you jerk very either forward suddenly or you stop suddenly. Okay. Antiderivatives help us take our units and they go the other direction. Okay, so if instead of wanting to divide by units of time, we want to multiply by units of time, and that's how units are impacted when we have antiderivatives. So that helps us accumulate things over a period of time. If you think of derivatives as looking at one instant of time, okay, what happened at time 4? Boom, just that specific instantaneous point of view. That's a derivative. An antiderivative will tell you what happened over the entirety of the period of time that you're looking at. It's an accumulation. So you can look at a very wide base of time or interval of time. So these are your clue words. If you are talking about cumulative, another word for that might be total, okay? It is always going to be connected to integration or an antiderivative. So those, if you pull those, what is the cumulative total of blank? And you think, oh, I see the word cumulative, therefore I'm going to be doing an antiderivative. Just like if you saw the word velocity or speed, you knew you were doing a derivative before. So in order for you to do a cumulative total, it must be a continuous function and a closed interval. That's what integrable means. If you see the word integrable, it means it is, number 1, continuous, and number 2, it has a closed interval, and it means it starts and stops. And it's not the same number. It's not from 3 to 3. Okay, it has to be from 2 distinct, from A to B. Okay, so here's a little, you glaze over, but let's read the words here. So Ian, can you read the words of the example down here?
Water is pumped into a tank at a rate modeled by WT equals T cubed minus T plus 2 gallons per water for 3 hours. Find the accumulated total amount of water added to the tank from time T is equal to 0 to time T equals 3.
Okay, thanks. All right, so we are given the word rate. The word rate is synonymous to the word derivative. And so the rate is this thing. This is already a derivative. Even though it says W of t, it is already a derivative. You can also tell it's a derivative because the units already have gallons per hour. And so that is also a clue that this is already the derivative. We are supposed to find the accumulation or the accumulated total, which means we need to find the antiderivative of that from time 0 to 3 over that interval. So our total is going to be found going from 0 to 3, and then we will apply the antiderivative. And you need a dt now, not dx, because the axis we're dealing with is time, not the x-axis anymore. So that's how you set that up. It is required that you write the integral down. No matter what method you use, whether you use antiderivatives, Math 9, or geometry, you have to write the integral. Okay, that's part of the rubric, and they'll be like, check, points, good, they wrote the integral down. Now you can use whatever method possible. All right, so fire that into a Math 9 if you're allowed, and then come up with a number. All right, let's see, I'll probably be faster than you guys. 0 to, let me put in 3. All right, I get 21.75. Your answer is incomplete unless you have units on it, and so then we want to make sure we attach units to our answer. The units are a multiplication of the 2 units that were given in the question. The 2 different kinds of units, we were given gallons per hour, and we were given hours. When you multiply gallons per hour times hours, the words together, the hours cancel each other out, and so we're left with an accumulated total of gallons. Yeah?
For a question like this, would we have to do this with my calculator?
If you did, the numbers would be easier. I'm not saying this is impossible, but on a quiz, we want you to be efficient on your time. Okay? All right, so here's another one. Okay, Matthew, can you read this one for us?
From 1970 to 1980, the rate of potato consumption in a particular country was functioned as C, and T equals 2.2 plus 1.1 raised to T millions of bushels per year, with T being years since the beginning of 1970. How many bushels were consumed from the beginning of 1972 to the end of 1975?
Okay. Couple things. Again, we have our clue words. We have the word rate, which modifies the C of T. So we know that this is already a derivative. The other clue is that it's in millions of bushels per year, and so then has the word per in it, so it is also a derivative. And we want to know how many bushels were consumed. Now the word accumulation is not in there, and the word total is not in there, but it's implied. How many bushels were consumed? How many total bushels of potatoes were consumed from the beginning? From the beginning of 72 to the end of 75. All right, anybody want to take a stab at writing the integral for this one? Brandon, you want to try it? Okay, write us an integral.
Would the interval be 2 to 5?
Okay, would the interval be 2 to 5? He's asking the question. Okay. What does T stand for? Read it for me. T is years since the beginning of 70. And how the question goes is consumed from the beginning of 72, but the other one says the end of 75. So what is the end of 75 really the same as? It's the beginning of 1976. Okay, so we would want to maybe change that to the beginning. Got to be careful about how you read. Okay, so the end of one year is the beginning of the other. And so it's not 2 to 5, it's 2 to 6. How do you think they would check this to see, to separate the people who are reading closely from the people who are not? Yeah, they would, as if this is a multiple choice, the 2 to 5 answer is going to be there. Okay? To catch the people who did everything else right but didn't get the upper bound right, as in opposed to the people who read 2 to 6. That's why multiple choices are so tricky, so tricky. Okay, keep going, Brandon.
And then parentheses 2.2 plus 1.1 raised to T, parentheses plus parentheses, and then dt.
Okay, great. So as soon as you have written your integral, then you're free to use whatever means necessary to solve that. So this would be another nice opportunity to use a Math 9. Okay, so 2.2 plus 1.1 raised to the power of x. And okay, so we get 14.692. Okay, so now we need to figure out what the units are on this. So we look at the comparison of what were the units on the rate and what are the units on the time that we're measuring. So my units on the rate are millions of bushels per year, and the time is being measured in years. So if we combine those with multiplication, what is left to be the unit on the total? Say it again. Millions of bushels.
14.7 bushels, that's it.
You're right. It's not just 14.7 bushels. It's 14.7 millions of bushels. So make sure your units are accurately representing. And a bushel is like a basket
Solid amount.
about this size. It's a bit bigger than a little bit bigger. It's like a small laundry basket.
14 million.
Bushels of
That's
potatoes.
that's a great unit. It's a small laundry
Okay.
basket.
Okay, in a physics sense, we can do integration on velocity to go back to distance. We last semester we did a distance equation and we did the derivative to get to velocity. Now we can start with velocity and do the antiderivative to get back to distance. Okay, that's the distance traveled. You have to be careful though about what it's asking. Sometimes they don't ask for the distance traveled. They ask for the final position, which is a different value. All right, so displacement is a combination of positive area and negative area altogether. Total distance is the absolute value of that, which we saw, that was like the words net and total that we saw. So think of this like net. And the other one is going to have the absolute value. So all negative sections have to be made positive. And then final position, you have to take into account where you started. Okay, so if Brandon's out there and he's running, say, the 800, okay? Brandon's displacement going around 4 times around the track, okay? 400, sorry, 2 times around the track. Okay, his displacement is how much? 0. Because he ended up at the same place that he started. Okay, but his total distance is not. His total distance is 800 because he covered all those meters as he was running. So make sure that you watch the difference on that. All right, so here we go. It's a little review from last semester and then a little bit from this semester. All right, we are given the velocity. This is already the derivative. This velocity equation is already a derivative. We can tell that because it's measured in meters per second. The particle time is going from 0 to 9. Use analytic methods, that means not your calculator, to determine when the particle is moving to the right, left, and stopped. Okay, so this is a review from first semester. How do you find when something is stopped? Set the velocity equal to 0. Do I need calculus to set the velocity equal to 0? No, what's the answer? 5. Okay, good. We're setting the velocity equal to 0 and we're getting 5. So we know that the velocity is stopped at 5. But we want to know what's happening before 5 and what's happening after 5. So remember our handy dandy little charts that we set up? Okay. So we are going from 0 to 5. And then we're going to go from 5 to 9 as the other side of our chart. And we're going to stop at 9 because that's what they told us to do. Now we want to find out if it's going to the right or to the left. So we're going to pick a value in the interval and we're going to check the velocity. Okay, we check the velocity, not the antiderivative, we check the velocity. So pick the number 1. If I put the number 1 in, what kind of velocity do I get? Positive. So this is positive velocity. If I pick the number 6, I get negative velocity. That answers the left or right question. So we know that we are going to the right first for a while because the velocity is positive, and then we are switching to the left. All right, now second semester question. Find the particle's displacement for the given time interval. So the definition of displacement is a straight out integral from 0 to 9 of 10 minus 2t dt. That is displacement. We can do this without our calculator, either with geometry, because it's just a 10 minus 2t line, or you can do it with antiderivatives, your choice. I'm going to go with an antiderivative right now, 10t minus t squared plus c on the values of 0 to 9. So that'll be 90 minus 81 plus c minus 0 plus c, so I get 9. Now I need units on that. And so if my velocity was measured in meters per second and my time was measured in seconds, then what is my displacement measured in? Meters. Okay, let's move on to the last slide. So if S of 0 is 3, now S is standing for the position. So that means the initial position is 3. That means 0 is the number of the number of seconds that has gone on, and 3 is the number of meters. That means this thing is not starting on the origin. It's starting with a 3 meter, think of it like a 3 meter head start, okay? And so final position is defined, we defined that earlier, as the addition of the initial placement plus the displacement. Okay, so the initial placement and then plus the displacement. So the initial placement is 3 meters, and then we just found the displacement is 9 meters. So the final position is it's 12 meters, okay? So you have a 3 meter head start, and then your displacement is 9 meters, and then you end up at the 12 meter mark. Now we want to talk about total distance. Total distance goes back to something we learned last chapter about what total means. When we talk about net versus total, we talk about also an integral from 0 to 9, but this time it is the absolute value of that expression, so 10 minus 2t. So not the parentheses of 10 minus 2t, but the absolute value of 10 minus 2t. You got to do this with geometry. Okay, you can't do antiderivatives with an absolute value without your calculator. If you got your calculator, okay, but without your calculator, you're gonna have to use the geometry on that. So this geometry, we are starting at 10, okay, and then we're just coming down with a slope of 2, and we cross here at 0 to 5, and then we end up at 9. Okay, so 0, 5 to 9, but 5 is where it crosses the x-axis. And so we have some values of this that are positive, but we also have some values of this are negative. So if you remember, what you've got to do is flip that, and you need to make that positive value here. So it has to be a positive absolute value triangle. So you've got two triangles side to side, okay? One triangle, the original positive one, and then we flip it. So using geometry, we know that the original first triangle, the yellow one, is 1/2 base times 5, height times 10. And then we want to add that to the new triangle, and its base is going from 5 to 9, so it only has a base of 4, and it's only going up to a height of 8. It was down to a depth of -8 down here. And so then when you make the absolute value, it's going up to a positive 8. So it's different, okay? We want it as a positive value. So we're looking at 25 plus 16. And so 25 plus 16, we're looking at 41, and that would be its meters. So we have a displacement of 9, a final position of 12, but a total distance of 41. So since the total distance is so much bigger, that means what this particle did is it went forward for a while and then it turned around and went backward. So it traveled a total of 41 meters, but part of that time it was traveling backwards. The time that it was going from 5 to 9, it represents backwards motion. So if we're talking about how many steps, we're counting on our step counter. The step counter doesn't matter if you're going forward or backward. That's called total. The displacement is actually, the position that you ended up in. So there is a difference between those two. All right, that's it. Good luck with this, and I will see you guys tomorrow.